Ancient mathematics could describe a line with no smallest part, a sequence with no final term, and a magnitude greater than any assigned number. It could not place these ideas inside one stable theory. Infinity appeared wherever a finite rule could be repeated without limit, but every proof still had to stop. The procedure could remain open. The argument could not. This tension existed before infinity became a formal mathematical object. Babylonian calculations used tables, reciprocals, and repeatable algorithms. Egyptian methods reduced practical problems to definite operations. Large numbers could be extended, and divisions continued. But surviving sources do not treat an infinite totality as available for calculation. An endless process could be indicated, not entered as a completed result. This is before logic, a history of rules before they were written. Greek philosophy gave this a vocabulary. The term apeiron could refer to what was indefinite, unbounded, or without fixed limit. In traditions associated with Anaximander, it did not yet denote infinity in the later mathematical sense. What lacked a boundary could be discussed without being measured as an object. Geometry placed greater pressure on that distinction. The side and diagonal of a square are finite, yet their ratio cannot be expressed through whole numbers. The recognition of incommensurability is historically uncertain. Its consequence is clearer. A finite figure contained a relation that no expected finite numerical ratio could exhaust. Ancient geometers did not answer with decimal expansions or algebraic notation. They reorganized the problem through proportion and geometry. Number and magnitude were treated through distinct structures. The objects were finite. Their relation resisted finite numerical expression. This was not yet endless quantity. It was a finite relation that no finite numerical scheme could complete. When division was applied to space and motion, the same pressure intensified. A bounded distance could generate an unbounded sequence of subdivisions. Zeno's paradoxes expose this directly. A distance could be divided in half, then divided again, with no final subdivision. Each stage was finite. The sequence was not. Motion appeared to reach an endpoint, while its analysis generated a procedure that did not terminate. Ancient philosophy had to account for completion without a formal theory of limits. Aristotle's distinction between potential and actual infinity became the most influential response. Potential infinity was not a completed collection, but the possibility of further continuation. A number could always be increased. A line could always be divided again. Actual infinity would require infinitely many parts to exist as a completed whole. Aristotle rejected actual infinity as a physical or mathematical object while retaining potential infinity within operations. The distinction imposed a rule on reasoning. Continuation was permitted. Completion was withheld. Greek geometry converted that restriction into method. If subdivision could not be completed, proof had to establish its result without completing it. The procedure, later called exhaustion, compared a figure with sequences of inscribed or circumscribed figures. The remaining difference could be made smaller than any assigned magnitude. The proof did not perform endless constructions. It showed that any assumed positive difference would conflict with a known relation. The process had no final stage. The proof did. Eudoxus is commonly associated with the method's development, although its surviving formulation appears mainly in later sources, especially Euclid. Archimedes extended related reasoning to areas, volumes, and curved figures. Later mathematics restated some results through limits and integration, but those concepts should not be projected backward. Archimedes had no modern real number system or symbolic limit notation. An indefinitely repeatable construction could support a finite proof without becoming an infinite object. Infinity remained in the rule governing continuation, while validity remained in a bounded chain of propositions. This stabilized practice, but did not settle infinity's status. A procedure could exceed every finite stage without producing an infinite totality. A magnitude could be divisible without containing a completed set of infinitely many parts. Proof controlled the operation by refusing to convert it into an object. Other traditions placed boundaries elsewhere. Atomists proposed indivisible bodies, while magnitudes remained divisible. Epicurean cosmology accepted an unlimited universe, and Stoic accounts distinguished finite bodies from unbounded void. Infinity could be admitted in one domain and restricted in another. Lacking decimal expansions, symbolic algebra, or a language for infinite collections, ancient inquiry kept magnitude, number, and cosmological extension in separate domains. Infinity crossed them without receiving a stable definition. Proof supplied the operative constraint. Every demonstration had to proceed through finitely many stated steps. An operation could repeat without limit, but no proof could consist of infinitely many unperformed acts. The unbounded process had to become a finite relation. The result was a durable asymmetry. The subject could exceed every assigned measure, while the statement remained finite. The construction could continue, while the justification closed. Ancient reasoning restricted infinity to positions where finite proof could govern it. The restriction was incomplete. Potential infinity did not determine whether infinite collections could exist as mathematical objects. Exhaustion established exact results without a general theory of convergence. Cosmological boundlessness did not define numerical infinity. Each domain remained stable by refusing claims its methods could not control. Infinity entered ancient reasoning as a managed instability. It was present in division, extension, motion, magnitude, and proof, but never under one formal definition. The system remained coherent only by separating what could continue from what could be completed. That separation protected ancient proof from contradiction, but also marked the edge of what its concepts could express. In the next episode, we will examine the structural limits of ancient reasoning.